Last time, we learned about the rotation matrix. The rotation matrix expresses the rotation of one frame, n, relative to another frame, m. The rotation matrix is a 3x3 matrix that tells us the projection of the x, y, and z axes in the n frame on the x, y, z axes in the m frame. We used a matrix like this to figure out the rotation of the end effector frame relative to the base frame in our robot manipulator. But rotation is not the only thing that happens to the end effector frame as the joints move in our robot manipulator. The other thing that happens is that the position of the end effector changes. The rotation matrix does not express how the end effector position changes. Instead, we have to use a different expression called the displacement vector. The displacement vector is represented by the letter D. The displacement vector only has one column and it has 3 rows. The first row tells us the x position of the n frame in the m frame. The second row tells us the y position, and the third row tells us the z position. Let me show you a couple of examples. Suppose that we have an XYZ 0 frame as shown here. Then suppose that I have an XYZ 1 frame positioned as shown here. From what we learned about rotation matrices last time, you probably recognize that the rotation matrix from 0 to 1 would be the identity matrix. What about the displacement vector? We want to know the displacement vector from frame 0 to frame 1. We know that this vector has to have 3 elements: the displacement in x, the displacement in y, and the displacement in z. Suppose that this distance in the x0 direction is equal to the value a. We would say that the displacement vector here is a, 0, 0. In other words, the displacement is a distance of a in the x direction, 0 in the y direction, and 0 in the z direction. Now, suppose that the one frame was instead positioned as shown here. And suppose that the distance here was represented by the value b. The displacement vector from 0 to 1 would now be 0 in the x direction, b in the y direction, and 0 in the z direction. Likewise, if the one frame was instead located here, and this distance was represented by c, then the displacement vector would be 0 in the x, 0 in the y, and c in the z direction. We can use this notation to represent the displacement between 2 frames in any combination of displacements in x, y, and z directions. The trick to getting this right for our kinematic diagrams is that we need to make sure that our displacement vector is correct, no matter what the values of the joint variables are. To help explain how this works, let's take a look at an example using a kinematic diagram. Here we have the kinematic diagram for the manipulator that we built on our board a few videos ago. Here we have a 1 frame that is positioned inside of a 0 frame. Could we find the displacement vector from frame 0 to frame 1? In order to do this, we need to find the distance in x0, y0, and z0, that is from the center of frame 0 to the center of frame 1. Right now, in this kinematic diagram, it looks as though the distance between the centers of these two frames is a distance of a2 in the x direction, 0 in the y direction, and a1 in the z direction. Right now, in this kinematic diagram, this vector is correct. However, consider what happens when theta 1 starts to move. When theta 1 is 90 degrees, the kinematic diagram instead looks as shown here. Now what is the displacement vector from frame 0 to frame 1? In this position, it looks as though there is no displacement in the x direction. There is a2 displacement in the y direction, and there is a1 displacement in the z direction. This displacement vector is different than the displacement vector we found when theta 1 was equal to 0. We can't have it be that the displacement vector is different for each value of theta 1. Instead, we have to write a displacement vector that will be correct no matter what the value of the joint variable is. To help us understand how to write this displacement vector, I'm going to draw this kinematic diagram from the top-down view, as if we were looking down at it from the top. If we were looking down at this kinematic diagram from the top, we would see the first joint from the top looking as though it were just a circle. We would also see some of the coordinate axes. We would see the x-coordinate axis pointing off to our right. And we would see the y-axis pointing straight up. We would not see z0 because looking down straight from the top, z0 is pointing straight at our eyes. It would look basically like a dot in the center of this joint. So I'm not even going to draw it here at all. Next, we would see the link A2 pointing in the y direction, like this. We would then see the joint 2 also looking like a circle. We would see the axis x1 pointing up like this. And we would see the axis y1 pointing to the left like this. We would then see the last link coming out like this with the end effector up here. We would see the x2 axis like this and the y2 axis like this. Looking down from the top, this distance here is the A2 distance, and this angle is theta 1. Now, could we draw this same picture the way it would look if theta 1 was 45 degrees instead of 90 degrees? Here's how the picture would look if we had an angle theta 1 of 45 degrees instead of 90 degrees. Remember that what we're trying to find out here is what is the displacement vector between the center of frame 0 and the center of frame 1. Using this picture, could we write what this displacement vector is in such a way that it would be correct for any value of theta 1? We could do that by identifying this triangle right here. This distance is the y displacement of frame 1 in frame 0. And this distance here is the x displacement of frame 1 in frame 0. So the displacement from frame 0 to frame 1, remember, has a component in x, in y, and in z. Can we write an expression for x, 0, 1? We can. It would be a2 times the cosine of theta 1. The value y01 would be equal to a2, that is the hypotenuse of this triangle, times the sine of theta 1. And the z position we can get from the kinematic diagram isometric view on the left. The z position is a1. Now, could we find the displacement vector d1, 2, the displacement of frame 2 inside frame 1? In order to do that, I'm going to ignore everything that happens before frame 1 and only look at the situation from frame 1 to frame 2. Suppose that we look down on this manipulator and look only at frame 1 and frame 2. We'll see joint 2 looking like a circle. We'll see x1 pointing up. And we'll see y1 pointing to the left. z1 is pointing up straight at our eyes, so that one will look like a dot, if anything at all. Right now, in this picture, the value of theta 2 is 0. What if we would draw the picture in such a way that theta 2 was 45 degrees? In that case, what would we see? We would see the link A4 coming off like this. And we would see the 2 frame looking like this. In this picture, this distance here is the link A4. And this angle here is the angle theta 2. Can we use this information to find the displacement vector from 1 to 2? Remember that we need an x value, a y value, and a z value. Since we know the angle theta 2, let's focus on this triangle right here. This distance would be equal to the y position of frame 2 inside frame 1. And this distance here would be the x position of frame 2 in frame 1. Can we use sines and cosines to figure out what those values are? The hypotenuse of this triangle is A4. So the cosine would be used to find x1, 2. And the sine would be used to find y1, 2. Finally, the z position of frame 2 in frame 1 can be found from the isometric view. The z position is A3. Now, we've found D01 and we've found D12. Could we use these to get the value D02? D02 is really the value that we're after. It tells us the position of the end effector relative to the base frame. When we learned about rotation matrices, we found that we could find R02 by simply multiplying together R01 and R12. It turns out that it does not really work the same way with displacement vectors. We cannot find D02 by simply multiplying together D01 and D12, or by adding them together. In order to link together displacements, we have to lump them together with the rotation matrices inside of a new matrix we're going to be learning about next, called the homogeneous transformation matrix. So for now, we're just going to do some more examples of how to find displacement vectors for some different kinematic diagrams. In the next video, I'll be giving you 5 examples of finding the displacement vectors for the 5 standard 3 degree of freedom manipulators.